Today we're going to see our first really, to my mind, remarkable result, really kind of amazing application of randomization in algorithms. So far we've been doing pretty basic stuff, sorting and median finding and stuff like that, but today something really that I think is really a surprising result. And it's based on the Chernoff bound, which is the final tail bound that I'm going to be teaching you. A quick check, how many people are already familiar with the Chernoff bound? Most. Okay, good. I didn't want to dwell too long on it, or rather, I didn't want to dwell too long on its derivation because that is for the most part boring math. Sorry, I also just landed from California and left my notes behind, so I'm lecturing off of my phone. So we've seen so far the Markov and Chebyshev bounds. Tail bounds. And the Markov is the most general, but also the weakest, right? But it's also the root of the Chebyshev bound, right? This is going to be a problem if it doesn't stay up. We essentially took the Markov bound and applied it to a different random variable, which was a function of the original random variable, right? And this is what gave us the Chebyshev bound. Here we took f of x equal x squared, right? Or x minus mu squared, right? And the Chebyshev bound gave us a tighter bound, one that depends on the standard deviation instead of the expectation, right? But it essentially is sort of an inverse quadratic bound, right? We had this sort of sigma squared over t squared kind of bound. This is an inverse linear bound. And if you think about sums of random variables and the central limit theorem, we know that in reality, you get things that look like a Gaussian, which decay exponentially away from the mean, right? Instead of linearly or quadratically. So these bounds are very far away from the true shape of the tails of a distribution. Okay. The Chernoff bound fixes this. So Chernoff, there are many bounds, many different formulations that are all called the Chernoff bound. Although it should be Chernoff bounds. Let's consider a bunch of our independent indicator variables with probabilities pi, respectively. They don't have to be the same. And in fact, I don't even care too much about what the PIs are. I'm just going to write the expectation of the sum is equal to some quantity mu, which of course is the sum of the PIs. The Chernoff bound says that the probability that x is bigger than 1 plus epsilon times the mean. And this already tells you we're going somewhere interesting because here we were looking at sort of large constant deviations from the mean. Here we're just looking at an epsilon distance from the mean, is less than e to the epsilon over 1 plus epsilon raised to the 1 plus epsilon power, all raised to the mu. Okay. What's important here is that this thing in the middle is a constant that is independent of mu and of n. It's also a constant that's less than 1. Okay? So what this is saying is that there is some constant which depends only on epsilon, right? Such that as the mean gets larger, the probability of deviation by epsilon from the mean decays exponentially with the value of the mean. And so in particular, if the mean is large, the chances of deviation are negligible. And even more in particular, for the kinds of algorithms that we're going to be looking at, once you get the mean to be log n or so, then you get an inverse polynomial here, and you can say that things are happening with high probability. Okay. And the Chernoff bound is, at least in my experience, the most commonly used deviation bound in the analysis of randomized algorithms. It works for almost everything. The proof uses the same technique as the Chebyshev bound of picking a function of the original random variable. It's all about picking the right function. And for each function you pick, you get a different tail bound, right? I can use x to the 4th or x to the 8th or some weird polynomial in x. They all give me tail bounds. Chernoff was the one who came up with the idea of using this particular function, which is called the moment generating function. The probability that x is larger than 1 plus epsilon times mu, I can apply any function to both sides, and in particular, I'm going to say it's equal to the probability that an exponential of the random variable, this is known as the moment generating function, if you've studied generating functions, is equal, e to the t times 1 plus epsilon times mu. Yes? Just exponentiated both sides. Okay. The next step is to use independence and write this, is to use the Markov inequality and say that this is less than the expectation of e to the tx divided by the expectation, or rather, there is no expectation on the other side, e to the t times 1 plus epsilon times mu. Yeah? This is just Markov's inequality. Okay. And now the final clever step is to invoke independence. Okay? We're not going to worry about the denominator for a while because it's constant. This is the expectation of e to the t times the sum of the xi's, which is the expectation of the product of the e to the txi's, right? But what's nice about this is that we now have a bunch of terms. Each depends on a single xi. Each is itself a random variable and is independent of all of the other random variables. So what do we know about the expectation of a product? Yeah?
If they're independent variables, then it's just the product.
Exactly. Now we use the fact that these xi are indicator variables. They can only take on values 0 or 1 with the corresponding probabilities pi. So I can write out this expectation, right? With probability pi, I get e to the t. And with probability 1 minus pi, I get e to the 0, which is 1. Yes? But now I'm going to reuse my, so this is sort of moving things over. This is 1 plus, well, let's just write it out, 1 plus pi times e to the t minus 1, just rearranging terms. Now I use my favorite approximation, that 1 plus x is less than e to the x. This is the product of e, or less than or equal to the product of e to the power of pi times e to the t minus 1. Now I've got a product of exponents. I'll turn it back into a exponentiating to a sum. But of course, the sum of the pi's is just mu. So this is e to the mu times e to the t minus 1. Did everybody follow that? Okay. So come on. So here I've got, this was the numerator of my quantity. You notice it has this e to the mu times something. In the denominator, I also have e to the mu times something, right? So I pull out the mu, and I get exactly the thing that I claimed. Sorry, I still have to fix t. So I can make I did this without specifying t. So what I get now is e to the power of e to the t minus 1 times mu divided by e to the t times 1 plus epsilon times mu, right? And this is true for any t. So I can use calculus to minimize it. It turns out that the right thing to do is to set t equal to the log of 1 plus epsilon. And when I plug in that t, I get exactly the bound that I claimed. All right? So there's two different parts of the Chernoff bound derivation. There's the clever part at the beginning, where you pick the right function and you use the independence. And then there's the boring part, which is just doing a bunch of math. And I'm sure you can check all the math yourselves, and it's written down in the notes as well. But are there any questions about either the clever part or the calculation part? Yes? Yeah, I don't know. Chernoff was a statistician, and I don't know how to think like a statistician. And so I don't know how Chernoff had this insight that the exponential generating function was the right thing to use. I'm guessing he did it, knowing that the answer should be inverse exponential, right? Perhaps guided him to think about using exponential functions. In a sense, these functions that you use are a way of shifting where you want to pay attention to things, right? When I use the quadratic function for the Chebyshev bound, I was sort of saying that I care more about farther away deviations. The penalty goes up quadratically, right? Because who cares? Like for Chebyshev, you're not trying to really get the bound to be really tiny, and so you can lower the penalty for things that are close to the mean if you can increase the penalty for things that are farther away from the mean, right? And so you could just say that Chernoff said, well, why don't I just make the penalty even more extreme, farther away from the mean, right? But I can't really know, okay? I'm trying to remember. I think I met his brother once, but I don't think I've ever met Chernoff. I'm not sure he was alive. All right. So moving on. This is a very general, very tight formula, but also one that's a little bit messy to work with. So as mathematically sloppy computer scientists, there's an array of simplifications that are usually good enough for our asymptotic results with their high probability bounds. first of all, the bound is less than e to the minus mu times epsilon squared over 1 plus epsilon for any epsilon greater than 0. All right? Because, and this is just because the log of 1 plus epsilon is less than 2 epsilon over 1 plus epsilon. But even that is still too complicated for us computer scientists. So the one that I preferentially use is that it's less than e to the minus mu epsilon squared over 3 for all epsilon less than 1. It's less than e to the minus mu times epsilon squared over 4 for all epsilon less than 2e minus 1. And it is less than 2 to the minus 1 plus epsilon mu for all epsilon greater than 2e minus 1. So these two together cover all possible values of epsilon. Yes?
I think Chernoff is still alive.
Yes?
102 years old.
Oh my, so I could still meet him, but I don't think I met him. I think I met his brother. I mean, they were both younger at the time. Okay, so why are these useful? Or why these three bounds in particular? Well, a lot of times we're working with very small epsilons. We want very small deviations from the mean, and for those, this is epsilon less than 1 is enough to pay attention to, right? And what matters is the shape of this bound, that it's sort of quadratic in epsilon and linear in mu. And that's what you sort of want to remember. This bound is a little bit weaker if you have to worry about epsilons that are a little bit bigger than 1. But once epsilon gets substantially bigger than 1, you no longer get a quadratic decay with epsilon. Instead, it becomes a linear decay with epsilon. So that's why you need these different shapes of bounds. Okay. General observation from looking at these bounds. Oh, there's a similar argument for the other tail. The probability that x is less than 1 minus epsilon times mu is less than e to the minus epsilon over 1 minus epsilon to the 1 minus epsilon, all raised to the mu power. So very similar to the upper tail, and you derive it in much the same way. But this, you only need one simplification, e to minus epsilon squared mu over 2, because you're never working with epsilon bigger than 1 for obvious reasons. So essentially, for small epsilon, you're looking at quadratic in epsilon and linear in mu, and there's just some question of what is the denominator on the term. Okay. Some general observations about this. Keep them on this board so that we have some spare boards for routing. First of all, notice that the bound sort of wears out when epsilon is around 1 over the square root of mu. Yes? That's where the exponent becomes a constant and your numbers are not going to be small. Okay? So if we plug that in, we're talking about the probability that x, I'm going to use some weird notation here, but hopefully it will make sense. Yes? Probability that x is outside of this range. Yes?
So essentially, like, this is where like epsilon is around the standard deviation.
Exactly. Right. So this is mu plus or minus the square root of mu. But what we've already seen is that the square root of mu, that's about what sigma is for coin flips. Right. So what this tells you is that the Chernoff bound starts kicking in when you're more than 1 standard deviation away from the mean. This makes sense because you are in fact quite likely to be about 1 standard deviation from the mean, so you're not going to be able to show that that is an unlikely event, right? So Chernoff only kicks in once you get into that unlikely territory of being outside of the standard deviation. Okay, make sense? As I said before, mu around order log n lets you say things are happening with high probability, because then you get a 1 over polynomial value for constant epsilon. Okay. Also, note the similarity of this bound to a Gaussian distribution. Right? A Gaussian distribution also has this, you know, e to the minus something squared parameter in it. So this is kind of saying that the tail bounds look like a Gaussian distribution's tails. Okay. All right. Any questions about this? Oh, sorry. One more thing I'll note. This actually generalizes to arbitrary random variables in the interval 0 and 1. Okay? So as long as the maximum possible value the random variable achieves is 1, right? As long as it's in this interval, it can be a continuous random variable with whatever distribution you like, and the Chernoff bound still holds. This isn't really very surprising because if you think about it, we're talking about large deviations, right? If you want large deviations, you kind of want to push as much probability mass to the edges as possible, right? And at least in terms of a single 0, 1 random variable, the way to push the most stuff to the edges is by having 0 and 1 be the only values that the variable takes on. Right? It's the most deviant of the variables that are in this interval. Okay? Yes? Yes, so that's absolutely right. If you have a random variable with any bound, right, some bound z, right, of course, if you divide by z, that random variable, all of your variables, then they become 0, 1 bounded, and that means that you can use the Chernoff bound. And what that means is that you need to throw another 1 over z into the mu term, right? Because you're also dividing the mean by z when you do that. And so that's sort of exactly the point, that the Chernoff bound is driven by how much each individual random variable in the sum contributes to the total of the distribution, or the total value. And as long as you have a lot of variables that are of the same magnitude, it doesn't really matter what their magnitude is, because no one of them can make a large contribution, and that makes the Chernoff bound apply. Make sense? Okay. So we are going to use the Chernoff bound over and over again. I recommend memorizing the simplified forms. I've never had to use the original form, the full form. But if you're working with really tiny epsilons and you need really tight bounds, you may need to do that at times. All right, so now we are going to switch to an application of this Chernoff bound, and it's really quite a marvelous application of the Chernoff bound. We're going to be looking at routing. Okay. We have a set of processors. And they have messages. These processors are connected in a network by links. This is, of course, what systems people would say. What we would say is that we have a graph, right, with nodes and edges. Right? We're going to say there are n of these processors. You'll see y is capital N in a minute. And we have a collection of messages that the processors want to send from sources to destinations. Okay. And they do that by sending them along paths made up of these links. Nothing surprising yet. Now we're going to particularize the model a little bit. We are going to say that we are considering a synchronous message passing model, which means that in one round, each link, or it's not personalize the links, you can move one message across each link. Okay. And so this is not really a good model of what's going on the internet, but it is a good model of what's going on in a multiprocessor or in a network of, a tightly coupled network of processors that are being used for supercomputing applications or data center applications. Since we can only send one message per round over a link, there's a problem if we are trying to send many, many messages over the same link, right? It's going to take a long time. I should state the obvious. We want to minimize the time to deliver all the messages. And intuitively, at least, this is related to the congestion on a particular link, which is just the number of messages that use it. Okay? So we want to minimize the routing time, and that pretty much means we're going, and we'll formalize this soon. This pretty much means that you want to minimize the congestion on links. Okay? So for those of you who took advanced algorithms, where you might think this is putting you in Maxflow territory, right? And you could imagine using Maxflow in order to compute optimal paths to send all of these different messages on. That doesn't work because you have multiple sources and multiple destinations, and each message has to go to the right. Each source has to go to the right destination, right? You can't lump all of your sources together into a single source and do a single Maxflow. This is what is called a multi-commodity Maxflow problem, because you actually care what gets where. And worse, it's integral, because you have to send a whole message. You can't just send half the message one way and half the message the other way. So you can't really use flow techniques here. You can use more sophisticated optimization techniques, but we're not going to. We are going to focus on oblivious. Actually, before I get to that, no, I'll put that down here. I skipped something. But, we're going to focus on oblivious algorithms that pick a message path, pick a path for a message without considering any other messages. Okay, so oblivious algorithms are, of course, much simpler to implement. If you think about it, if you want to do some sort of non-oblivious coordinated routing, it requires that the processors talk to each other in order to find out what the other messages are that need to be delivered. How are the processors going to talk to each other? Well, they're going to have to send messages. So it becomes sort of a circular problem if you use a non-oblivious algorithm. Okay. Now, I will also point out that sometimes there is no way to minimize, to get small congestion on a particular set of messages. Can anybody think of an example where you're just going to be stuck having a huge number of messages traverse a single link? Yeah? Yeah, if you have all the messages coming from one place or all of the messages going to a single place, then you're really out of luck. There's going to be congestion at the origin or at the destination. But that's kind of an annoying case to think about because you can't do anything interesting with it. So we are going to focus on permutation routings. Okay. Each source and destination has exactly one message. Okay. One message starts at each source, and each node is a destination for a single message. So what you actually have is a permutation between the sources and the destinations. Now, you can work on this problem, and people have, for any shape of network. And the technique that I'm telling you about is actually pretty general. But in order to make it concrete, we are going to look at the hypercube. This was one of several very popular networks used for multiprocessor machines. And it's sort of typical of those networks. And the kind of argument that I am making here applies for all of the popular networks. But we can limit the notation if we fix our attention on a single one. So what is a hypercube? It's something that that many of you are probably familiar with. It is, well, best described by a picture, right? So you have hypercubes of different dimensionalities, right? D equal 1, 2, 3, 4. Oops. Let's try again. 0, 1, 2, 3, and so forth. And one way to think about these hypercubes is that each node is an integer. Sorry, a d-bit integer. And you have links if the integers differ by 1 bit. Okay. And this means that the number of nodes that you have is exponential in the dimensionality of your hypercube. Okay. So the question is, what can we say about routing on this hypercube? Well, for deterministic algorithms, we're immediately in trouble. Okay. There's a theorem that says that any oblivious deterministic routing algorithm for degree D network permutation routing has congestion at least omega of square root of n over d in the worst case. So takes that long to route. So let's think about what that means for the hypercube, okay? D-dimensional network, so this is something like 2 to the d over 2 or so as the routing time for permutation routing on the hypercube, right? That seems way worse than you would hope for, right? What would be the most obvious lower bound for routing in a network? Yeah? Not every pair, but it is a permutation, so each node is a source and a destination for something. That's going to be less than 1 usually, because there are generally more edges than nodes, right? Yes? So that is true that could be true for a specific network, but what would be if you just looked at a network, what would be a property of the network that would immediately give you a lower bound on the routing? Suppose my network was a line. Would I expect to be able to route quickly? Why not? Yes?
Because there's like essentially a choke point of like upside one.
Suppose I just were going to send one message before we get to the congestion. Yes? Yeah, exactly. So the diameter is obviously a lower bound, right? Because sometimes you want to send a message from one side to the other of the network, right? But in the hypercube, I mean, the reason we like the hypercube as a routing network is that it has very low diameter, right? What is the diameter of the hypercube? Yes. Why? Exactly. So one path between a pair of nodes in the hypercube, this is not the only path, but one path between the pair of nodes is the path where you just look at the difference in bits between the source and the destination, and you correct the bits to change from the source integer to the destination integer. And each time you change a bit, that corresponds to sending that message across a particular link, right? So this tells us 2 useful things. First of all, it tells us that the hypercube has diameter d, which is log n. And it also introduces us to this bit fixing routing algorithm, right? So is a natural routing algorithm on the hypercube. Right? And it immediately proves that the diameter is d. Convenient that I chose d as the letter for the dimension. And that's just log of the number of nodes. So it's a very tight network. It can move data between lots of nodes at very low diameter. Okay, but it's not clear how, because this is exponentially worse than the diameter, right? Okay, so no deterministic algorithm, in particular, if you use this bit fixing algorithm, right? This gives you an oblivious routing strategy, right? There are cases where it is going to take you about root n time to move those messages, okay? So that's pretty bad. And you'll prove a special case of this in the homework that I will put out later today. Let me emphasize, though, that this bound applies for all networks, not just the hypercube. It's a very general bound. Okay. But we're looking just at the hypercube and asking, at least for the hypercube, can we do better? Yes? Degree, sorry. Right? Degree d. Fortunately, on the hypercube, the degree is d. So d stands for dimension and degree and diameter. It's very convenient. Okay. Sometimes English works out well. Okay, so what's the caveat? What do we change in order to beat this bound? Well, we get rid of the deterministic part. Right? So turns out that using randomization, you can achieve order d for permutation routing. Exponentially better than what you can do deterministically. Okay? And this is not wacky theoretical order d. This is actually something that is used in practice at times, okay? Or at least used to be. It's so simple. Okay? The analysis is where things get interesting. And the reason randomization works is that one of the things that I listed in my description of why you randomize, how it helps you, is load balancing, right? We've already talked about balls and bins. You throw n random balls into n random bins. Each bin gets very few balls, okay? We are going to apply that intuition here. If you can somehow create random paths, then each edge is going to only get a few paths. Now, it's not immediately clear how we do that because the source and destination are fixed. So how are we going to create random paths? But trust me, we'll get there eventually. Okay? So in order to get there, I'm going to start by, again, assuming something that I said we would never assume in this class, which is that the input is random. Okay? In particular, I'm going to start out by analyzing what happens to your congestion and routing if you consider random destinations. Okay? So there's still going to be one message at each source, but its destination is random. Okay? Now, this almost certainly makes it not a permutation, right? It's very unlikely that your random choices end up with exactly one, each destination used exactly once, right? Some destinations will probably be missed, and some destinations will probably be used multiple times. And if you have a destination being used multiple times, that would seem to push up your congestion, right? But even so, we're going to prove that this works out well, okay? And the proof is very simple. It doesn't actually require any math. I'm going to let t of ei be a random variable equal to the number of bit fixing paths. We just described the bit fixing algorithm that use edge I, or edge ei, or link ei. Okay. So I'm studying random destinations with this utterly trivial bit fixing algorithm. Okay. So how do we analyze T of ei? Well, we can look at each edge, right? Look at each source, and compute. It would seem we need to work out the probability that this source decides to use this edge, which is going to be determined by which destination is chosen by the source, right? And this is very dependent on what is the source and what is the destination, and it's very messy. So we're not going to do that at all. Instead, we're going to argue like physicists. I actually have a physics undergrad degree before I decided it was too hard. And just say that by symmetry, all the T of ei are equal. Okay. This hypercube is symmetric in every possible way, right? You can permute. You can permute the dimensions and switch the zeros and the ones, and it's still the same hypercube, right? So so this follows. Does this do I need to dive into this at all, or yeah? You can fix them in whichever order you like. This argument is still true. No, what I'm going to do, so think of it a different way. I'm going to say that I'm going to fix the bits in order 0, 1, 2, 3, 4, right? Just in increasing order. But when I fix a bit that does not change, it means I just don't move the message in that round. Okay? So each message does something in each round, but half the time it's just going to stay still. Okay. Any other questions? Okay, so given that we have symmetry, can we somehow evaluate the, the random variables are not the same, but their expectations are the same. Okay. The variables do have the same distribution, but what's important is that their expectations are the same. Okay. Notice also that the expected length of message path is just what? So I have a message, starts at a particular node, has a random destination. What is the expected length of the path? Yes. D over 2, right? Because I'm picking a random number for the destination, each of its bits has a 50-50 chance of being different from the source number, right? So I can now say that the sum of the T of EIs is equal to the sum of all the path lengths, right? It's two different ways of counting the edges, right? I either count path by path, adding up all the edges on the path, or I count by edge, adding up all of the paths on the edge, right? Which is just n times d over 2, right? Sorry, need some expectations here. Right? Which tells me, by symmetry, that the expectation of the congestion on an edge is d over 2. Everybody agrees? Question? Oh, did I lose a factor of 2? Let's see. I could just throw some O's in, and then you wouldn't be able to ask me anymore, right? Oh, sorry, the D. You're right. Yes, sorry. There are ND edges, right? So the expected congestion is a half, not D over 2. Yes? Correct. So right now I'm just talking about congestion. I'm not talking about routing time, right? I'm just saying how many paths go through the edge, not when they actually, not when the messages traverse it. Okay. Yes? Yeah, I think the less messy analysis allows, right? Again, if you think about how you would actually implement this, you don't want the two sides to have to talk to each other to decide whether they can talk to each other, right? So it's easier to just have two unidirectional links, one in each direction, and that's why you get ND rather than ND over 2 edges. Okay. Yes. Omega square root of whatever d.
Yes.
Is this like for the No, no, no. This is saying that there is some edge that will have, right? Again, this is a worst case argument. This is saying that whatever your oblivious routing algorithm is, there is some permutation that causes some edge to have this amount of congestion on it. And therefore, the messages that want to use this edge are going to need to wait, right? And so the time that it takes to route everything is going to be lower bounded by this. Yes? Okay, so this actually already takes us to a pretty good stopping point. Because if I tell you that the expected congestion on an edge, on each edge is a half, now notice, so that, again, expectations aren't enough here, right? We're worried about lots of different edges, and maybe even though the expected congestion on an edge is only a half, there are so many edges, some of them are going to deviate from their expectations. Maybe I still get into this worst case situation of a root n lower bound. Okay? No, that is not what happens. Because now I can note that T of EI is a sum of indicator variables. Can anybody confirm that? What are the indicator variables that define T of EI? Yes?
Whether pass I uses, whether I say pass J uses like edge EI?
Exactly. Right? Or sorry, well, I won't say path, I will say x sub source. Right? Each source is sending a packet. It picks a random destination, which may or may not use edge EI. Yes? So, T of EI is just the number of sources that decide to use edge I, right? And so it's a sum of indicator variables. I have no idea what the probability distribution of those indicator variables is, because I did this silly symmetry, I did this crazy symmetry argument, and so I got the expectation without knowing anything about the individual variables. So all I know is this random variable is a sum of indicator variables and has small expectation. What can I do now? Sum of indicator variables with small expectation, and I want to bound the deviation from expectation. What should I do? Chernoff, right? I'm going to say the probability that T of EI is bigger than some log n. Right? Why am I picking log n? Well, we'll see when I get the bound. Which of my bounds do I use if I'm trying to get a bound of log n or so on the deviation? Yeah? Yeah, this is many times the mean, right? This is a very large epsilon, right? So this is less than, I'll put it in quotes here, 2 to the minus 1 plus epsilon mu. Yes? Let me put a k here. What is 1 plus epsilon mu? Well, notice, this is what's nice about this bound. This is just the value itself, right? The value in the exponent is the quantity in the limit that you're looking at, right? So here it's just 2 to the minus k log n, right? N to the minus k. Yes? In other words, we can now say with high probability, no T of EI exceeds order log n. But notice that order log n is just d in a hypercube. Question? Constants. No constants in this class. Okay? So everybody accepts this? Okay, so now we're basically done. Okay, I can now do a very straightforward, a very sloppy analysis, right? So if T of EI messages use edge EI, then no message is held up more than T of EI steps there, right? In the worst case, all the messages arrive at one side of T of EI, and they all want to use it at the same time, and so one of them has to wait until all of the others have gone. And this is going to take you T of EI time, right? So the total delay for a message is at most the sum on its own path of the T of EI variables. Yes? Now we said that its path has length at most d, right? Because of our bit fixing algorithm, right? So this is order d log n, which is order d squared or log squared n, with high probability. Okay, so if the destinations are random, then the utterly simplistic bit fixing algorithm achieves a routing time of log squared n, square of the diameter, which is exponentially better than what deterministic algorithms can achieve. Yes? Yes. Well, exactly. Congestion is defined in terms of path counts and is not specifying at exactly which time different messages are going to be using that particular edge. It's just which messages are going to use that edge at all. Sorry, this one? Yeah, that because you prove a high congestion. You prove that. I don't remember the details. You will after you've done your homework. I think you're actually proving a congestion more like root n and then arguing that, but I'm not sure. It may be that you're just showing the congestion itself has this quantity. Okay, and then there'd be another d factor maybe in reduction in the routing time. Yes? Good. Why did I choose this bound? Why didn't I use, log n? I've just done an example of the kind of shortcutting that will become second nature in randomized algorithms, but let's unpack it. Yeah, well, if I used log n here, I'd have a probability of 1 over log n instead of a probability, or 1 over log n to the k instead of n to the minus k. Why do I want to have a quantity like big N to the minus k? Yes, in the back. Sorry, you in the white. Where's the union bound? Exactly, right? So, and again, this is why this with high probability language is so useful, right? What I proved here is that a particular edge has low congestion with high probability, right? But over here, I went and said that all of the messages, or that all of the edges have low congestion. What's the bridge? The bridge is that I apply a union bound of this statement to all of the edges. How many edges are there? Well, n times d edges, right? So I need to make my probability small enough for the union bound to be small, right? But if I set k equal to 2 or 3, right, so that I get a 1 over n cubed here, right, then the fact that I am taking a union of 1 over n cubed over nd edges still gives me a value that is polynomially small. right? And this is again, this is the usual story with high probability. I can set whatever constant I want here in order to make this polynomial as small as I need it to be so that the union bound stays polynomially small. And if it turns out I need the union bound to be smaller, I make that happen by choosing an even bigger constant here, if I'm going to be taking later a union of union bounds or something. Okay, but this all gets swallowed up in the with high probability with just polynomially small probabilities. Okay? So, this has sort of cracked the main difficulty of the problem. We've gotten this polylogarithmic bound, which is so much better than what you can get deterministically. There are some details. One is that this is only about random destinations, right? I said you can't count on having randomness in your input. We need to introduce the randomness in our algorithm. So what are we going to do if the destinations are chosen deterministically and badly? Okay? That's one thing I have to fill in for you. The other thing I'm going to do is show you that this bound is actually loose, that if we're actually just a little bit more careful in our analysis, we can drop this bound from log squared n to log n. So we can get a routing which is just a constant multiple of the diameter and is therefore asymptotically optimal. Still just using bit fixing. This is the same algorithm. It's just the analysis that needs to be improved. Okay? So let's take a short break, and then I'll do both of those things. All right, let's resume. Just two logistical things. One is that I have to run immediately to a stack of meetings right after class, and so there's going to be a slight delay in the posting of the homework. It will show up later tonight. So you should look for it on NB if you already want to start working on it. The second thing is that there is no class on Friday. I'm sure you're all very sad. So you should have fun. Actually, with the time that you save, I'll recommend one other thing. If you like the way I teach algorithms, you should come see how I teach country line dancing. I am teaching a country line dancing class at the Wellness Center every Sunday from 5 to 6:30. It is open to all MIT students. It assumes no experience whatsoever and requires no special talent because country line dancing is actually pretty easy. but it's also a lot of fun. We've had about 25 people coming, and there's room for more, so come give it a try. Yes? 5 o'clock until 6:30, that's right, in the Wellness Center on the 3rd floor of the Student Center. Okay. All right, so a few things left to clean up. Actually have to backtrack first because I got overeager and stated something that we haven't actually proven yet. If we want to take the really simplistic perspective, we have to be a little bit careful about the interactions between things. The simplest way to apply what we know here is to think about phases of the algorithm where we fix one bit at a time. So first, we run the algorithm to correct all the first bits. And the question is, how long is it going to take to correct just the first bit of every message? Well, that depends on the congestion of the edge that's being used to fix the first bit. And we just argued that the congestion of that edge is order log n, and therefore we can say that the time to fix the first bit is only log n. Then we start the second phase, same argument. It takes log n time to fix the second bit, log n time to fix the third bit, so on and so forth. And that is where I'm crossing this out because I haven't actually done that analysis yet, although I'm about to. Okay? Instead, we just think about phases, fix each bit. So log n time per bit, log squared n time in total. Okay. Now, I do want to argue that the actual time to fix is the sum of the congestions on a specific path. That's not necessarily the case if I use the phased argument, but if I just use a more greedy approach, if I do FIFO routing, where I send a message as soon as I can. So if a node has a message waiting to traverse a link, then it sends a message across that link. If there's more than one message that wants to traverse the link, the rest have to wait. But at least one message is going to traverse the link if there is a demand for that link. And there's no waiting for phases. Okay? So now I claim, and this actually requires proof, that the total time spent waiting for a packet is, at most, the sum of the congestions on its own path. Okay. So the intuitive story here is that there may be other messages that are crossing paths with this one, but each message only holds you up one time step. We have to prove that. Okay. But it kind of makes sense, because like if the message holds you up, then it's in front of you, and that sort of suggests that when it's going to stay in front of you, right? It's like, and so it won't hold you up again. But it's more subtle than that to actually prove it. Okay? And so that means that the total delay is the sum of the T of EIs. Yes? Now, what can we say about the expected value of the sum of the T of EIs? We don't have many tricks in this class. We've already seen all of them. Yeah? Exactly. Sum. And how much is that? Well, what did we say was the expectation of a single edge congestion? 1/2, right? So this is at most d over 2. Yes? Now, I'd like to make the same argument that this random number is a sum of indicator variables, right? Because then I could use a Chernoff bound. Yeah, question? No. I'm sorry. I'm talking about sort of each node has a collection of messages in a round that are waiting to progress, right? And so the point is that if there's a message that wants to use an edge, well, there may be multiple messages that want to use the edge. You pick one of them, the first one that you've got that you received, and you send it on. Okay? So that's what I mean about a node going a message going as soon as it can.
Oh, okay.
That's right. Okay. So there's a little problem with my argument about sums of indicator variables here because I don't know I claimed that the total wait time was the sum of the congestions, but the congestions on different edges of my path aren't independent of each other, right? If my path is very congested on this edge, then that suggests that it's going to be very congested on the next edge as well, right? So thinking about a sum of these T of EIs, right? Each T of EI is a sum of indicator variables, but the sum of those sums is not made up of independent, if I look at it that way, is not a sum of independent indicator variables, right? So I can't use the Chernoff bound. Okay. But I can be a little cleverer about this. So the problem is that T of EI are not independent. However, let's consider, I need another letter. So I have a particular source, and let's ask, let's make an indicator variable Cij is 1 if source J's message collides with source I's message. Okay? In other words, do these two messages, do their paths ever converge? Okay. The Cij are independent. Right? Because each of the destinations is being chosen independently. So if I know that message 2 runs over my path, it tells me nothing about message 3. Yes? Okay. I'm not getting any questions, so I'm assuming this is all perfectly clear. So I'm just going to keep going. My claim is that the total delay is equal to the sum over j of the Cij's. Total delay for I is the sum over, right? This is the claim that I made up here, right? And this is less than the sum of the T of EI's, because if an edge has a certain number of messages congesting it, there have to be at least that many paths, right? So this counts each path that collides with me once. This counts each path that collides with me, the number of edges that it collides on. So this is an upper bound. So now if we put expectations around this, we find out that the expected number of paths that collide with me is at most d over 2, okay, which is log n over 2, right? Yes? Yes. So remember, I'm saying here, this is an indicator variable that is 1 if if j's path collides with me, right? This is counting the total number of other packets that use the same edge as me on the various edges of my own path, right? And so if a path collides with me, this is going to count the number of edges that we have in common. And this is just going to be 1. So that's why this is upper bounding this. Okay? Question? That is the claim, and actually I used the wrong notation here. But that's exactly what I was saying up here, that when I said the intuition here is that each message can only delay another message at most once. Okay, that's an intuition, but numerically, it actually is formally true. The total wait time for a packet is less than the number of other paths that collide with it. In other words, each other message that collides with me only adds 1 to my delay. And I have to prove that to you. Okay? But if it's true, then the total delay is this sum of indicator variables. Its expectation is less than this expectation, which I showed to be small. Again, I don't know the probability distributions for the individual indicator variables, and I don't care. All I care about is the expectation of the sum. Okay? So I have a sum which is about log n. What do I do now? Well, I do the same thing as I did before, right? I apply a Chernoff bound, right? The probability that this quantity is larger than some k log n is less than or equal to, well, I go back and look at my bounds. So now my expectation is no longer a half, it's log n over 2. But if I set epsilon equal to 3 or 4, I can still use this bound, right? And at that point, I get the same result as I did before, right? So I still have the case, right? So if I set epsilon equal, I use the Chernoff bound with epsilon equals 3, and I find out that the probability that I'm bigger than, let's see, if epsilon is 3, it's going to be 3/2 log n, right? Is less than n to the minus, no, let's make epsilon equal 6, so that this is 6 log n, and now this is less than n to the minus 6, right? And now I have the same high probability claim, that with high probability, no message collides with more than 6 log n other messages, and therefore, because of this lag argument, with high probability, every message is delayed at most 6 log n steps, and therefore the maximum routing time is only 6 log n. Okay? All right, so that got rid of the log square and pushed it down to a log. Still, 2 things left. One is to prove this lag argument. I'm going to do that on Monday. You don't actually need it for the homework, or you can look in the notes. But I will do the other thing. How do we deal with not having random destinations? Yes, a question?
So if we're saying that
Exactly. We show a high probability result for a single message, and then we apply a union bound that applies to all messages. Okay. Notice that we're now taking a union bound over messages as opposed to a union bound over edges, but there's only n messages, so it still works fine. Okay. All right, so I finished with the coolest trick. This is due to Valiant and Brebner. Valiant is a very big deal professor at Harvard. And they worked out this analysis, but they also figured out how to apply this to deterministic destinations. Okay. We have a technique that's great for random destinations. What do we do if our destinations are not random? Yes?
you split the algorithm into 2
Exactly. What we do is we're given a deterministic set of destinations. We send the messages to random destinations instead. Okay? So given destinations, choose random detour destination for each. And then route each message to the detour. And then route each message from the detour to the destination. I claim that we have already analyzed this. Why? Yes?
Because in each step, there's like one, okay, it's like, let's just like think of the first step, sources.
Yeah, well, the first step is what we analyzed, right? We analyzed this.
And then the second step is the recursive analyze, which is basically the same as what we
Exactly. The second step is just saying if you have random sources going to your deterministic destinations. But all of our analysis was in terms of just which paths lay over which other paths and things. And so it's symmetric about, right? You need one endpoint to be random, but it doesn't matter whether it's the source or the destination endpoint. So this is Valiant Brebner routing. Send the message to a random place and then send it to where it's supposed to go. And this achieves asymptotically optimal routing for any input permutation on the hypercube and on a much larger class of networks, right? Trivial algorithm, clearly very practical because you're just doing bit fixing in each step, right? All of the complexity is in the analysis, right? Which is what I love about randomized algorithms, is that you can do these incredibly simple seeming things, and if you study them hard enough, you discover that they work really well. Okay. All right, I will see you all Sunday at Country Line Dancing.